pictures from the book where they define critical point and they talk about the second derivative test. So critical point is when the first and second derivative, or first derivative with respect to x and with respect to y are both equal to 0. Or actually, I didn't mention this last time, but it also could happen when the partial derivatives don't exist. And that's the same. That's more like the definition from Calc 1, because we have to allow for when the derivative doesn't exist, like the absolute value has a critical point at the point of the v, and all that stuff. Second derivative talks about your scenarios, and down below they have a couple of notes. In the case of C, it's called a saddle point. We called it a saddle point already in our notes last time. If D is equal to 0, then the test has no conclusions, no information. It could be a local max or a min or a saddle point. And then here they talk about that determinant formula for the discriminant. Do they call it discriminant? They just call it D. Oh, determinant. Yeah. So this is from your textbook, and this is the first step is knowing this. Second step is to try to apply it to what's really going on. So let's do a problem. And there's an interesting problem in the book. I don't know if it's in your homework. And in this particular problem, you're kind of forced to look at not just the function, but the graph also. So you're kind of forced to look at the graphical point of view as well. So let's first look at it from a graphical point of view, and then we'll see if we can do the analysis on the actual function here and come up with the same results. It says here to use the level curves in the figure to predict the location of the critical points of f and whether f has saddle points or local max or mins at each of the critical points. Then use a second derivative test to confirm your predictions. All right. Now, when you're looking at a level curve like this, contour curves, you're pretending that this is on a mountain. That's really the best way to try to visualize this. Here you have a mountain, and we have 3.2, 3.7, 4, and then 4.2 on this side. It looks like 4.2 goes up like this. 5 and 6, so it gets higher as you go this way. Maybe just for fun, we'll draw some gradients here, but we'll do that later. There's a couple of distinct features here that we should be watching out for. Any ideas what they might be? Do you know what I mean by distinct features?
Well, the line that which it changes from an increasing slope to a decreasing slope.
Okay. Where it looks like it goes from an increasing slope to a decreasing slope. So the idea is that at some of these points, if you go along the x, we should see it increase and then decrease. Along the y, we should see it increase and decrease. So in terms of looking at this picture, what points should I be focusing on? There's 2 points that actually give different features of the graph. So 4, x equals 0, and what? Y equals 0. So at that point 0, 0 would be an interesting thing to look at. So let's look at this for a minute. And it looks like if I'm going along the x-axis here, we have level curves. Well, I'm a level curve at 4 right now. If I go this way, it looks like I'm going to go level curve at 3.7. If I go this way, it looks like I might be going level curve at 4.2. So that doesn't look like, it looks like I'm going from lesser to that and then to a higher. So it doesn't look like it's a critical point, but it might be still. And if we do the same thing going along the y, we're kind of getting the same results here, the 3.7, and then up this level is 4.2 again. But there is something interesting. If we go this way, this is at level 4. If we go this way, it looks like it's at 3.7, and we go up to level 4, and then we go down here at 3.7 again. So there's definitely something interesting going on at that point. And likewise, if we go this way, we see 4.2, 4, and then this 4.2 wraps around over here. So it looks like this thing goes from lower to high to low. So it looks like, imagine an upside down parabola. And then over here it goes from high to low to high again. So imagine a right side up parabola. So I'm kind of looking at this, and there's a good possibility that this is probably going to be a saddle point. And we'll get confirmation of that when we actually do the second derivative test. So it looks like 0, 0 would be a good candidate for a saddle point. Let's put it down here and then say this is a saddle. But we'll confirm it. Now it looks like there's another special point on this graph. Can you point it out? Think about level curves and think about how the contours of a mountain would look like. Where are the peaks of the mountain? Where are the high points and where are the low points? Anna? At the point 1, 1? That looks like an interesting point. So what happens here is that if I go further away from here, I'm going to be at 3.2, 3.2, 3.7, 4. It's what? So it looks like this is going to be a valley, a local minimum, and then as you go further out, you're going to go up. So in any direction you go here, it looks like the level curves are going to give you higher and higher values. So this 1, 1 looks like it's going to be a local min. Okay? So those are some key features. Think about the x's when you're looking at level curves. If you see x's like this, it's kind of like an x. Those are good candidates for critical points and saddle points. If you see holes, enclosed figures, ellipses, circles, things like that, those are also good candidates for local max and mins. And you just need to look at the levels to determine whether it's a maximum or a minimum. All right, now let's do the analysis part. Let's take this function and go through the process of finding critical points and then using the second derivative test. So we need two things to begin with. We need the critical point. So for the critical point, we need two things. We need the first derivative with respect to x, and then we need the derivative with respect to y, and then we're going to set both of these equal to 0. All right, so it seems like an easy task, and sometimes it's easy, but there's going to be times where it's going to get really tricky, so you're going to have to just be careful about doing this. If you have a graphing program like Graphing Calculator that I have, you might be able to have a good chance of figuring out what the critical points are. But the algebraic way of doing things could get a little tricky, so just be careful. With respect to x, the derivative of 4 is 0. We got 3x squared, and the derivative of y cubed is 0, and then we have 3y. So derivative with respect to y, 0, 0. We got 3y squared minus 3x. So we have 3x squared minus 3y equal to 0. And if I take the 3's out, divide by 3, and then maybe solve for this, y is equal to x squared. That looks like it's a weird relationship, but at all these points on your xy plane in your domain, at all these points, you're going to have your derivative with respect to x is equal to 0. So we do the same thing over here. 3y squared minus 3x equals 0. And so again, we take the 3's out, and then x is equal to y squared. So at all these points in your xy plane, when x is equal to y squared, we have your derivative with respect to y is equal to 0. So what you want to do is you want to combine them somehow. And this is where it gets algebraically tricky, and you may have to get creative. In this case, we don't have to get too creative. We just take one that's already solved for and put it into the other equation and see what kinds of relationships we can get with x and y. So I'll take y squared and put it in for x here. X is equal to y squared. And then I just solve for y in this case. It looks like I have one variable now. So y is equal to y to the fourth. And you might think it might be good to just divide out by things, but you have to be careful when you divide out by things, because it could be 0, and we don't want to divide by 0. So whenever we get something like this, we want to bring everything on one side and factor. So let's bring everything over to let's bring it to the right side. Y to the fourth minus y is equal to 0, and then factor. And then you get a couple of solutions here. Y cubed minus 1, you just have to make sure that if you need to work things out. If it's y squared minus 1 is equal to 0, then you'll have two solutions there. But in this case, it's y cubed. I only get one solution. One real solution. There's other imaginary complex solutions that exist. But we're not talking about that. Here, we just have these two. And then from here, we put this back into the thing that we replaced it with. So when y is equal to 0, x is equal to 0 as well. So we get the point 0, 0. That's this point right here. And then when y is equal to 1, we put it back into here. We're going to get x is equal to 1 squared, so x is equal to 1. So we get the point x is equal to 1, y is equal to 1. So note that even if I'm dealing with squares, I'm not finding the plus and minus of things, right? Because I'm looking at it. I'm looking at only two solutions, 0 and 1, and I put that each in turn into the original equations, and then I found one other point, or one other value for x, one other value for x, and then so I only get two pairs of numbers. Okay, so that's the first step, finding critical points. I got two critical points. Now for each of these critical points, what we want to do is we want to run it through a discriminant machine, the function machine where we get the discriminant. So we need to find the discriminant. And if you remember the formula, it's fxx, fyy minus fxy quantity squared. So we just go back to our fx. We want to take the derivative of fx with respect to x. So the first one is derivative of this with respect to x is 6x minus 0. fyy, the derivative of fy with respect to y, looks like it's 6y. Minus, now I take either one, the derivative of either one with respect to the other variable. So let's take fx, take the derivative of this with respect to y. It looks like I'm going to get -3. And then according to my D formula, I want to square that. So this turns out to be basically 36xy minus 9. Okay. All right, now I'm going to take the 2 points that I got and then test it. So let's take 0, 0 first, and I want to put that into my D function that I just created. So I have 36x times y minus 9. So x is 0, y is 0. And so this turns out to be -9. Oh, I don't even care what it turns out to be. All I know is that this is less than 0. That's what I was really going for. So according to our second derivative test, this is a saddle point. So we're done with that. Our other point is 1, 1. So we'll find 1, 1, 36 times 1 times 1 minus 9. So 36 minus 9 is, I don't know. I don't care. It's bigger than 0. That's all I care about, right? So if it's bigger than 0, I have to check one more thing. And so I have to go back to fxx, which we found to be 6x. And then I want to put in that point 1, 1 in there. So there's no y's, but that doesn't matter. There is an x that we put in there. X is equal to 1. There's no y. And again, I don't care what this value is. I just care whether this is positive or negative. And in this case, it's positive. Boy, I'm starting to cough, too. I had a bunch of sick students in my previous class, and a couple here, too. I don't know. I know there's one sick person, though, sitting over there. Where else? But she came up and talked to me. So fxx is our other check that we do to, if we have the discriminant to be positive, we have to check the sign of the first upper right-hand corner of that upper left-hand corner of that matrix. And we see that we get a positive discriminant and a positive second derivative. And if you look back in the notes, positive, positive gives you a local minimum. And that's what? So that is our solution. We confirmed it. We looked at it in the graph, and then we confirmed it using our second derivative test analysis. Okay? Any questions about this? All right. Let's take a look at some more of these things that might be a little bit more challenging. It's going to give us the same thing. Find the local max and min. If you have a 3D graphing software, graph the function with a viewpoint that reveals important aspects. Okay, well, let's try this one. This one is non-polynomial. It has an exponential function. It has a trig function. Let's see if we can make sense out of this. So the function is this thing. We can skip the graph idea and then just go ahead and try to find the critical points. So let's find the critical points. We do that by finding the derivatives and then setting them equal to 0. So with respect to x, the cosine y is constant, and I just have e to the x. So this is 9 e to the x cosine y. Nothing really happened there. With respect to y, the cosine is the variable. The e to the x is constant, so I have a 9 e to the x. The derivative of cosine is negative sine. And I have to set each of these equal to 0. So when they're set equal to 0, I have a product, so I can separate this. I have e to the x, or 9e to the x, doesn't matter, but e to the x will never be equal to 0, so I don't think that'll happen. And then the cosine of y equal to 0 when, does it have a domain here? It'll equal to 0 at infinity, but we're not gonna include that. And it just means it looks like it'll flatten out at infinity, but we're not interested in that. Okay. Pi over 2, positive, negative, plus minus n pi or something like that. So we have a bunch of critical points here. Let's check this one going to 0. And then we have e to the x at 0 again, which will never happen. Sine y equal to 0 when y is equal to 0 plus or minus n pi. So it looks like it'll be 0 when y is equal to 0 and y is equal to all that other stuff. So the idea is to try to find x's that would associate with this. So let's just try pi over 2 when y is equal to pi over 2. What does x have to be? X has to be 0. It could be anything. So there's no restrictions on what x is. So x can be anything. So this would lead me to believe that there's not one particular critical point there. Kind of like a critical line. But when y is equal to pi over 2, y is equal to 0 for this one, for example. These two things are not equal, and so it doesn't look like we're going to find critical points here. In other words, you can't have a point that would have y is equal to pi over 2 and y is equal to 0 at the same time. Because you want fx to be equal to 0 and fy to be equal to 0 at the same time. And the only way that will happen is that if y is equal to pi over 2 and y is equal to 0 at the same time. So I don't think this thing has any critical points. Oh, that's what happens when you mess around with like exponential functions and trig functions, and weird things happen. So if there's no critical points, then we're probably not going to see local max and mins and stuff. Let's see what the answer is. I'm supposed to put DNE if it doesn't exist, huh?
Figured out that when you can multiply stuff out, you can just write down like all the things that you multiply. You don't have to do it.
Oh, you don't have to multiply it?
You can just write what you have to do, and it will mark it as right.
Yeah, that's the thing about not having to simplify. In this case, you don't have to simplify it. They actually take a look at your expression and parse it through a Wolfram a Mathematica processor to see if it's the same. All right. What happened? All right. So we do have a graphing program, so why don't we take a look at this graph and see what happened to this that made it kind of seem weird. So f of xy is going to be represented by our z. Is equal to 9 e to the x times cosine of y. And this is this is a view that's going from -2 to 2 in the x, y, and the z, so I probably want to zoom out a little bit, see if I can find anything. I'm not really finding too many interesting things out of this. It looks like if I follow along an x or a y value, I see little valleys here that might have represented those places where the derivative of with respect to x is equal to 0, or maybe the derivative with respect to y is equal to 0. But aside from that, I'm not really seeing any places here where it would logically look like a max or a min. What would be a good view of this? Maybe right. Oh, maybe that was it, huh? No. That looks weird. Oh well, that's what we're. Just going to take a shot to put in our notes. All right, it's kind of hard to pinpoint the different aspects of this, x's and y's and stuff. So maybe we'll just go on to do another problem. You guys okay with this? Should we do another example? Whatever everybody else wants.
Is it going to be on the quiz?
No, not this one.
Okay.
So the quiz is going to be on
The stuff we learned Wednesday, Thursday, and beginning of the episode. So it starts with
directional derivatives and gradients.
Up until right before optimization.
Gradients, yeah. So so your quiz will be in directional derivatives and gradients. That's section 6, 12.6, 14.6?
If you go, it's just like the Wednesday notes.
Yeah, just the notes from Wednesday and Thursday.
Wednesday and Thursday.
And Monday.
And
Half of Monday, something like that.
So all 14.6 then.
Well, maybe we'll do one more problem, because I feel like there's some other times where we have to find critical points, and they're a little bit more complicated than what it seems. So let's see if we can stay away from trig. All right, let's try this one. This one has an exponential function, but it also has some polynomials here. So let's take a look at this to see if this will give us a good variety, a good other type of problem. So our function is 8e to the y times a y squared minus x squared. So let's go through the process of finding the critical points, and then once we find, if we find any critical points, let's run it through our second derivative test. So fx, the e to the y is constant, so imagine foiling this out. You'll see that the e to the y times y squared will disappear. So I just have a negative 8e to the y, and then the 2x. So let's make the 8 into a 16. So 16 e to the y times x. Fy is something that we will have to use a product rule. So let's treat this as two different functions that we're multiplying. So the derivative of the first times the second plus the first times the derivative of the second. So the derivative of the second is just 2y. The x squared will go away. And then in a lot of cases, you don't really care about simplifying, but in this case, since we're going to set this equal to 0, we probably do want to go take the time to simplify a little bit. And I will combine a couple of things and separate. So imagine foiling or distributing and then combining, and then you can redistribute or undistribute or just keep it the way it is. So I have an 8 plus an 8, that's 16, e to the y. I can't combine that. Never mind. Yeah. Can I do anything with that? Only thing I can think about doing is maybe factoring. This is exactly what I wanted to do, but I think this is the only thing I can do. So I got y squared minus x squared and then plus 2y. All right. So now let's set each of them equal to 0. I have fx equal to 0. 0 is equal to minus 16 e to the y x. And I would set each of these terms equal to 0, each of these factors equal to 0. And we know that e to the y is never going to be equal to 0. And so I have x is equal to 0. Now I have this thing equal to 0. And I'll set each of these equal to 0, but I know that this will never equal to 0, so I'll just not worry about that and just focus on y squared minus x squared plus 2y equal to 0. Now I have these two things that are happening at the same time. I want these two equations to be happening at the same time. So it looks like I can just say x is equal to 0 all the time, and in fact I can put that into here, into the second equation. So I have y squared minus 0 plus 2y is equal to 0, and then now I'm left with a y. So again, we want to factor. We don't want to divide anything out by y. So factor 1 plus, or y plus 2 is equal to 0. So I have y is equal to 0 and y is equal to negative 2. Okay. How many critical points do we have? 2 critical points. So I need an xy for the critical point. So what's my x for the first critical point? 0, comma 0. And then next one, 0, comma negative 2. All right? So this is good. It has a different feel from the other critical points that we saw earlier. And the idea is to make sure to combine both when fx is equal to 0 and when fy is equal to 0 when you're solving for these critical points. And it has to satisfy both equations at the same time. Okay, now let's get to our D. So fxx, and we want to take the derivative of this thing with respect to x. Oh, this isn't going to be easy. I need more room. Let me do it in pieces and then combine it later. So fxx, derivative of this with respect to x. Now that's just going to be negative 16y, or e to the y, times x. And so negative 16 e to the y is constant. The derivative of that is just the constant with respect to x. fyy. I would probably want to take the second one over here that's slightly more simplified and take the derivative of that. So the derivative of this will be product rule. Derivative of the first times the second plus the first times the derivative of the second, 2y plus 2. And if all you're doing is taking derivatives, you'd be done, except we want to simplify this because we're going to work with it. And so let's factor out an 8e to the y, and then let's combine things that we can combine. So I have y squared minus x squared, and I can combine the 2y plus 2y. That's 4, right? 4y. And then I have one more constant, the plus 2. So it looks a little bit nicer to deal with. And now I have to do fxy. So fxy, I can either take, so fxy is equal to fyx. I can either take the derivative of fy with respect to x, or I could take the derivative of fx with respect to y. And fx looks a lot simpler. If I take the derivative of that with respect to y, it's just going to be itself again, right? And if I were to do the derivative of fy with respect to x, I should get the same answer. Yeah. All right, so our d function looks like it's going to be complicated. So fx, x, negative 16 e to the y, fx, fyy, 8 e to the y times this whole big mess. Minus fxy squared. So this negative is going to be a positive after you square it. And I guess for now we can leave it like that. Oops, I forgot the square. Yeah, I'm not very interested in simplifying. Maybe just simplify this. This is going to be a positive since we're going to square it. But there's a negative out here still, right? So keep in mind that there's still a negative here. I think you should try to simplify it if you can. I'm going to go on from here. Say d is 0, 0. To check my first critical point. And 0 in for x and for y. I'm going to get a 0 in for x. Should I do this in my head? So e to the 0 is 1. I have negative 16. I have 8 times 0. E to the 0, which is 1, so 8 times 1. I have 0 plus 0 minus 0 plus 2. So I have that part. And then x is equal to 0, so this whole second part disappears. What do we have left? We have a negative 16 times positive 16. So negative and positive is negative. I think this is going to be a negative. So it looks like we got ourselves a saddle point here. So it looks like we got 0, 0. And then they say they want us to give a three-dimensional point. We've been dealing with two-dimensional points. How do we make this a three-dimensional point? The original problem, plug it back in there. Right? So 0 for x, 0 for y, that will make this parentheses 0. And it doesn't matter what that first part is, because it'll just be 0. Oh, I don't want to use up that space. I'm going to have the graph up here. All right, we got a saddle point. Now let's check this second one. We'll put 0 in for x and negative 2 in for y. So 0 in for x, negative 2 in for y. We got negative 16 e to the negative 2. We have 8 e to the negative 2. Now I have to do negative 2's multiplied a bunch of places here. Negative 2 squared minus 0, x is equal to 0, plus 4 times negative 2. Well, you really have to watch out for that negative 2. Plus 2. Minus, and again, x is equal to 0, so the second part will just disappear. So I have negative 16 e to the negative 2. I know that first one's going to be negative. Now let's see what happens here. So whatever is happening in the parentheses is going to tell us what's happening for this whole expression. So I have a 4 minus 8 plus 2. What is that? Negative 2? Negative 2. So it's a negative. So we have a negative times a negative is a positive. So now that that's the case, I have to go back and check. We have to go back and check what happens to fxx. So fxx, evaluate this at 0, comma, negative 2. fxx is this. There's no x's, it's just the y. So I have negative 16 e to the negative 2. E to the negative 2 is always positive, so this is just going to be negative 16 times some positive number. So it's going to be a negative. So we have a negative for d, we have a positive for d and a negative for fxx. What does that say? Local max. All right, our local maximum. There's no local min. We have a local max at 0, comma, negative 2, comma, whatever that z is. Yeah, whatever that z is. Okay. So let's check our answers, and then let's sketch the graph. Zero, comma, negative 2, comma. If I put 0 in for x, I have negative 2 squared is 4 times 8 is 32 times e to the negative 2 power. Do they want? I think they don't talk about decimals here, so you may want to keep it the way it is. Yeah. So we have a saddle point at 0, 0, 0, and we have a local maximum somewhere. Well, while it's thinking, let's see if we can put in our Is wrong? Oh. Let's graph it. Z is equal to 8e to the negative y squared minus x squared. What is it?
It's not -1. E to the 1. Oh, you're taking that 1 point?
Oh. Well, here's that minimum right here. No, it's a maximum. That's what we got, right? A maximum? So it has a maximum here, and it looks like a saddle point over here. So let's just, there's something wrong here. What's wrong? Oh, maybe that's all they're asking for? Why would they not ask for the third component for that one? How can you tell?
It says so right there at the very top.
Oh. All right, let's start simplify. 8 times e to the -2 times -2 squared minus 0. That seems silly. But we took away the z point, and then it didn't give us... What? 0, -2 is wrong? Zero, -2. Let's put, what was it? 32 e to the -2. Looks pretty right to me, sitting up there. What? Practice another version. Oh, it's going to take too long. Here, why don't I just... What number was it? 8. Uh-oh, we're wasting too much time here. We need to take a look at boundaries, too. Oh, they just want the value. Oh. (32) times e raised to the -2. Yeah, because y is -2, right? Oh, so here's a lesson for us. They say maximum value. They want the actual value. They don't want the point. And so when they want the actual value, you just give them the z value. So the local maximum value, just the z value. Saddle point here, they actually ask for an x, comma, y, comma, f. So that's your z. So here you actually want to put in the things. So that's what they were looking for. Whew. Man. So 32e to the negative 2. This is the only thing that they want. All right. So that's looking for local max and mins. Now in Calc 1, so let's see if we can backtrack and I'm going to put the little picture here later. But in Calc 1, there is this theorem called the extreme value theorem. Anybody familiar with the EVT? Okay. So the extreme value theorem says that you attain f is nice and continuous, then you attain a global maximum. Now, if you have like a parabola, it's clear that you have a local and global minimum at the bottom of the parabola. But then the maximum, there's no local maximum because your parabola goes on forever. But if we close your domain, then the parabola is eventually going to stop at a particular height. So if you imagine your parabola going from -1 to 2, you're going to be guaranteed a global maximum. Even if this didn't have a local maximum, you're going to be guaranteed a global maximum because you stop it somewhere and then you close it. If it's open, that's a different story. We don't have a maximum. But since it's closed, you're going to make sure that you will have a maximum and a minimum value. So that works the same way for surfaces. So functions, if you have a function going from R2 to R, you'll be guaranteed, as long as f is continuous and all that, you will attain a global maximum and minimum. Now, the global maximum or minimum might be a local maximum or minimum, or it could also happen in the boundary. So a simple example that they have would be like a paraboloid. So if you have a paraboloid, technically this paraboloid can go on forever, right? But if you give it a boundary, if you give it like a square boundary in the bottom, then you're not really going to see your whole paraboloid. You're only going to see a piece of it up to the boundary. And now that you have a piece of it up to the boundary, you can see that there are local or global maximums in that boundary. Okay? So what do we have to do to find our global max and mins, we basically, back in the old days in calculus, what we did was we found critical points and then endpoints. So we found critical points and then endpoints, and then we plugged it into the function to determine what your heights are, and then you decide which one's your least and which one's your greatest. That would be your global max or min. So the same idea is going to go for here. We're going to find critical points. And then we're going to check the boundary. Now, the boundary, since it's we're talking about a two-dimensional domain, your boundary is going to be a little bit more complicated. So your boundary is not just going to be endpoints like this, where we just pick your x is equal to something, x is equal to something as your endpoints. Your boundary will actually be a two-dimensional curve, or several two-dimensional curves. Let's put the S in parentheses. So it could just be one curve if it's a circle or an ellipse, or it could be two or three or four lines or something like that. So we have to check the boundaries. So we check the critical points and then the boundaries. So this is where it gets a little bit more complicated. All right, let's see if we can grab an example in a minute. We have a minute left. Boy, we wasted too much time on that problem. All right, let's take a look at this, number 16. I think this is hopefully easy. Find the absolute value, absolute maximum and minimum values on the set. So what we have to do is we have to look at the set in 2D. 0, x goes from 0 to 4. Y goes from 0 to 5. So your boundary is actually consisting of 4 line segments, and you have to check these 4 line segments. So what you want to do is you want to take a look at this function, f of x, y, and then we have to check it on those boundaries. Well, first we have to check to see if there's any inside of this thing, because you're looking for your maximum and minimum that's either on the boundary or inside. So we need fx, 4 minus 2x, fy, 6 minus 2y, and then we set them equal to 0, so this is finding the critical points. So if we set this first one equal to 0, we get 2, x is equal to 2, set this equal to 0, y is equal to 3. So we have one critical point. So is that critical point inside? So that critical point is in here. So we want to check this critical point when we basically want to put it into the function. And then what we want to do is we want to check to see if any part of this boundary, if your function will dip down or will go up high. All right, this is going to take a while. So I think we need to be done for today. We're going to pick up from this example, and we'll do this, and then we'll find another way to find max and mins using this thing called Lagrange multipliers. Ooh, that's going to be hard. Yeah, could be. All right, see you guys tomorrow.